This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, we will explore light cones and, most importantly, time travel. In previous videos, we have discussed several strange effects caused by the speed of light being constant in all reference frames. One of them, the relativity of simultaneity, seemed to violate causality since the order of events became relative, meaning that you couldn't determine which event caused the other. If we are to understand time travel, we must first solve that problem. Let's begin with light cones. We will first draw the world lines of two particles of light, both crossing the origin but moving in opposite directions. These world lines create the shape of two cones on the graph, called light cones. The upper cone is called the future light cone, since it is in the future from the perspective of the origin. Everything within it represents what an event at the origin can affect. The lower cone is called the past light cone, since it is in the past from the origin. Everything within it can affect an event at the origin. Any events outside of the light cones cannot influence or be influenced by the origin. They are called space-like events. Events within the light cones are called time-like, and events on the world lines are called light-like. Because of mass-energy equivalence, nothing with mass can travel faster than the speed of light. For this reason, information from one spacetime event cannot travel faster than the speed of light to affect another event. This preserves causality. Space-like events cannot influence the origin, and origin cannot influence them. You will notice that all simultaneous events are space-like, even in other reference frames, since information would have to travel at an infinite speed to reach the origin from them, or vice versa. This is the same reason why, if you see something, you technically saw it as it was slightly in the past, since it took time for the light to reach your eyes. Also notice that, whenever simultaneity changes, the space axis rotates above or below the other event. That is what causes changes in the order of events. If we took a light-like event, the space axis would have to tilt 45 degrees for that event to become simultaneous. But only a theoretical reference frame moving at the speed of light tilts 45 degrees, and since that is impossible due to mass-energy equivalence, causality is preserved. If we take a time-like event, causality is only further preserved since one would have to exceed the speed of light to view the event as simultaneous with the origin. With this in the back of our minds, we can now discover how to travel forward in time. The answer to forward time travel lies in a thought experiment called the twin paradox. Imagine that there are two twins. One leaves Earth in a spaceship, turns around and returns. When they return, the twin that stayed on Earth would be older than the twin who left, revealing that the twin in the spaceship traveled into the future. As we addressed in the last video, this can't be caused by time dilation, since different reference frames disagree on who is moving. If we are to find the real solution to the twin paradox, we will need to model the situation on a spacetime graph. Let's draw the world line a spaceship moving close to the speed of light. Halfway through its path, it instantly reverses direction, but continues at the same speed. Now we add the space axes before and after the velocity switch. In the context of the twin paradox, these are often called planes of simultaneity, since everything on a line is simultaneous in the reference frame it represents. You will notice that, in the direction of the acceleration, there is a chunk of time the spaceship never experiences, since it never views anything within that time as simultaneous to it. Since it skips all of that time in a single instant, the spaceship travels into the future. In reality, instance velocity switches are impossible, since they would require infinite force. But large enough accelerations can simulate this effect, causing time to speed up rather than skip. That, right there, is how actual forward time travel works. The greater an object accelerates, the more time seems to speed up for it. What's interesting is that the rate at which time speeds up from a given acceleration is not constant. Instead, the greater the distance between the object accelerating and the clock it is referencing, the more time will speed up for the accelerating object. This solves the twin paradox, since the spaceship twin traveled through time when they accelerated back towards Earth. While they accelerated away from it to start going and to stop, the twin was much closer at those times, and so time wasn't slowed down enough to cancel it out. This means that every time you accelerate relative to a galaxy far, far away, you travel into the future. Future time travel, though, is only observed in the direction of the acceleration. Now, for the more controversial one, backwards time travel. In the opposite direction of our spaceship's acceleration, something strange happens. The planes of simultaneity intersect. This suggests that the object would view events it already experienced a second time over, traveling backwards in time. But that would break causality. If you went backwards in time, nothing would stop you from changing past events. This threat to causality has the same solution as the last one: light cones. You will notice that all past events are space-like, so they can't affect or be affected by the spaceship. Instead, in the opposite direction of its acceleration, time would only slow down at an increasing rate with distance. You have now completed special relativity. In the next video, we will begin exploring general relativity, eventually completing Einstein's theory. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire!